The father of the hydrogen bomb said that abandoning thorium was a mistake, and that a nuclear reactor running on thorium instead of uranium fuel would give us enough energy for thousands of years. And yet today, it's nowhere to be seen. So what went wrong? And with several companies speculating it is possible, is thorium poised to make a comeback? Let's dig a little deeper and find out what's really going on. Welcome everyone, my name is Michael, and there's been growing interest in a type of nuclear power that was first investigated in the 1950s and then essentially abandoned: thorium. Still, advocates say it's a superior alternative to uranium reactors operating today and seriously worth a second look. Like uranium, thorium is a heavy element mined from the Earth that can be used in fission reactors, much like the ones we already have today. Both are used in a controlled chain reaction that creates heat and then spins a steam turbine and a generator to make electricity. From a practical high-level perspective, there is very little difference between uranium and thorium. The details are in the nuclear physics. Very simply, uranium undergoes the fission chain reaction directly. A uranium atom is struck by a neutron and fissions, releasing energy and additional neutrons that go on to strike other uranium atoms. Thorium, however, doesn't directly fission when it is struck by a neutron. Instead, it absorbs the neutron and then converts itself into a uranium atom. Then, when this new uranium atom is struck by a second neutron, it fissions and releases heat. This may not initially seem as efficient, but it turns out it is possible for much more of the thorium in a reactor to undergo this conversion to uranium and then fission, compared to trying to fission the uranium atoms directly, as is done in conventional reactors. This means that instead of extracting less than 0.5% of the available energy in a conventional uranium reactor before the fuel is thrown away, advanced thorium-fueled reactors should be able to extract 40 or 50 times that amount of energy, meaning they're potentially much more efficient with the fuel. This means it requires much less mining and would make much less nuclear waste, one of the biggest downsides of using nuclear energy in general. It's because of this fuel efficiency, among other claims of improved safety and reduced nuclear waste, that advocates say that we should be giving thorium another look. But if thorium is so great, why don't we really see more plants using it? Or anybody using it? Well, it turns out we did use it. At least we tried. From 1965 to 1969, the United States operated what's called the molten salt reactor experiment at Oak Ridge National Laboratory. At the time, there were concerns about limited uranium supplies amid the expansion and construction of nuclear power plants that would consume the world's uranium reserves within a few decades. The idea was to explore options to use alternate or more efficient fuel sources like thorium. The creative design of this experiment used molten salt, or a liquid fuel, with mixtures of uranium and thorium rather than the solid fuels of conventional nuclear plants. The liquid fuel was pumped through the reactor where it generated large amounts of useful heat. The molten salt reactor experiment was more or less a success, demonstrating that thorium could be used as a viable fuel. Glenn Seaborg, the scientist who discovered plutonium and the chairman of the U.S. Atomic Energy Commission at the time, called it a success. Yet just a few years later, in 1973, the Atomic Energy Commission largely suspended funding for thorium reactors in favor of other designs that showed more promise at the time. So what went wrong? While the experiment demonstrated the feasibility of a thorium molten salt reactor, several problems with the design were found. The largest issue had to do with the integrity of the metal pipes that held the liquid fuel. A metal alloy called Hastelloy N was used to contain the fuel salt in the molten salt reactor experiment. Testing of the Hastelloy N surveillance specimens produced cracks in the grain boundaries of the salt-exposed surfaces. Because of the depth of the cracking observed, the MSRE would not be acceptable when extrapolated to the 30-year design life. Essentially, fission products in the liquid fuel were attacking the pipe, causing surprisingly deep cracks to occur, and the metal wouldn't last as long as they would have needed in a much larger plant. This meant that any design couldn't be viable until further research into the materials could be done. The second major issue was the production and release of the highly mobile and radioactive isotope tritium. Because of the complex chemistry of using the liquid fuel, tritium production was fairly high. And because tritium particles are very small, they are very hard to contain, resulting in the unexpected release outside the reactor and into the environment. Once outside, tritium often finds its way into the groundwater, where it can be detected using only specialized equipment. And if it is consumed by people by drinking the water that is contaminated, it can lead to a variety of health issues. Now, to be fair, the molten salt reactor isn't the only reactor design that produces tritium. Several operating plants, such as those in Canada, produce a fair amount of tritium, but over time they have learned how to manage it. Because of these issues, and a general focus on other designs, progress on the thorium reactors largely stalled in the US for the next 50 years, resulting in little attention outside the scientific community. However, in the past decade, things have changed. Renewed interest in nuclear power has also led to investigating alternative designs and fuels like thorium. Despite the challenges of the past, a number of companies and government research projects have started up recently to say that thorium deserves a second look, that the technology has advanced enough in the past 50 years to make it a viable alternative to the uranium-dominated nuclear industry. China is the furthest along, having started up its liquid-fueled thorium molten salt reactor in late 2022. The 2-megawatt test reactor is actually based on the US molten salt reactor experiment, but hopes to demonstrate that the technology has progressed, and will actually lead to a much larger plant by 2030. China is also simultaneously building a solid-fuel pebble-bed thorium test reactor designed to determine the viability of this alternative approach. This means China is actively funding and building at least 2 different reactors based on thorium designs. India is another, and in an interesting position, having the largest thorium reserves in the world but almost no uranium. Unlike many other countries, thorium reactors have been part of India's plans for decades to take advantage of this. The government adopted the 3-stage plan in the 1950s for long-term energy independence. The first stage was heavy water reactors, which was accomplished initially through technology from Canada and then later domesticated. This has been a success with over 20 reactors operating and 10 more under construction. The second stage is breeder reactors, the first of which is expected to come online in 2023. These reactors are designed to produce plutonium to feed the third and final stage, using that plutonium to start reactors that eventually run entirely on thorium. However, this initial plan was enacted back in the 1950s and still has a ways to go. Because it will still take many years until it is fully on a thorium cycle, the Indian government has designed the Advanced Heavy Water Reactor as a parallel path. Although not a pure thorium reactor, it runs on mixed fuels, getting about 40% of its energy from thorium. This allows India to lessen its dependence on imported uranium and rely more on its own domestic thorium supplies. On the commercial side, several companies are fighting for position to create attractive designs. Somewhat similar to the Chinese test reactor, a company called Flybe Energy is designing a liquid-fueled thorium reactor that it says is inherently safer, simpler, allows online refueling, and produces 10,000 times less waste than conventional reactors. Also descended from the same molten salt reactor experiment, Flybe expects its design could take full advantage of the thorium cycle, allowing it to operate extremely efficiently, and claiming a person's entire lifetime would fit into a piece of thorium the size of a golf ball. Thorcon is another company looking to design liquid thorium reactors, but their approach is to try and leverage the existing efficiencies of shipbuilding techniques. The idea is that by using existing components and manufacturing technology, the reactor could be built entirely at a shipyard and then transported to wherever it is needed. After 8 years, the reactor would be shipped back to the facility for refurbishment and relaunch. Taking a slightly different approach, Copenhagen Atomics is looking to use existing stockpiles of spent nuclear fuel alongside thorium. Although to be fair, the spent fuel that they are referring to is mostly separated plutonium, but the marketing sounds pretty good. Nonetheless, the liquid fuel design concept should fit neatly into a standard 40-foot shipping container, which would allow for rapid deployment, particularly in remote locations. And these companies may clearly be onto something. Thorium provides an alternative fuel source to conventional uranium, more than doubling the availability of the raw fuel supplies. Add to that the extreme efficiency of the designs, which means the existing fuel supply could literally last thousands of years. Combined with other advantages and technologies, these designs can go further to improve safety and reduce nuclear waste. Another advantage should be the cost. Based on the efficient use of the fuel, the ongoing costs associated with obtaining more thorium should be much lower compared to conventional uranium plants, which need regular shipments of fresh fuel. And with many thorium designs operating at atmospheric pressures, construction should be much simpler as well. An analysis found the levelized cost of electricity for a general thorium molten salt reactor to be $53.51 per megawatt hour, compared to $63.08 for a conventional nuclear plant. For their floating design, Thorcon estimates the reactor to be between $30 and $50 per megawatt hour, depending on the size of the plant. Keep in mind that wind and solar range from $30 to $40, so even with the advantages of thorium, these plants are still likely to be more expensive than renewables, and they haven't been commercialized yet. However, if you're curious about levelized cost of electricity and why cost isn't everything, you should check out the video on small modular reactors. I'll leave a link down in the description. There are, however, still some challenges when it comes to using thorium, particularly in its liquid form. The issues of cracking and corrosion on the piping have greatly been reduced, but haven't been demonstrated over the full lifetime of the reactors. Many designs also need complex chemical processing to separate out the good fuel from the waste products, and all that liquid material is highly radioactive, meaning it is difficult to treat, and accessing components for maintenance becomes even more of a challenge. Even minor spills of liquid fuel could be extremely difficult to clean up. The problem of tritium production also hasn't gone away. Although certain methods can reduce the amount, it still poses a highly mobile danger, and clear environmental limits need to be set and followed. Finally, compared to the existing conventional reactors running on uranium, which together have accumulated over 10,000 years of combined operating experience, thorium reactors have collectively operated for really only around 50 years, if that. And most of these are small test reactors. This means the knowledge, training, experience, and infrastructure for fuel and components is not nearly as well known for thorium, leaving it vulnerable to surprises, even if things look very good on paper. A growing group of advocates claim we made a huge mistake turning our backs on thorium, saying that it was abandoned because it wasn't good for making nuclear bombs, and that it's actually safer, more plentiful, and makes less waste than conventional nuclear plants using uranium. But how much of that is actually true? Let's dig a little deeper beyond the surface hype and find out what's really going on. The 1950s and 60s saw the US under substantial pressure from the international competition in the field of nuclear power. The UK got the first full-scale commercial nuclear power plant in 1956 at Calder Hall, and the Soviet Union anticipated it would have multiple plants generating thousands of megawatts from a variety of different designs. In order to stay competitive, the US Atomic Energy Commission kicked off the Power Demonstration Reactor Program, which provided government funding for private companies to make nuclear power a commercial reality. This included a variety of designs, including thorium, which in 1962 was loaded into the first cycle at Indian Point, a plant not too far north of New York City. However, the second core a year later abandoned thorium and was replaced with conventional uranium. But why? The answer was given in 1963 at the International Atomic Energy Agency's Conference on Operating Experience. When asked directly, "Can you tell me why you changed your plant over from a thorium to a uranium cycle? Is the reason purely economical, or did you expect trouble from the use of thorium?" The reason is purely economical, and we did not expect to have any trouble with the thorium cycle. It is hoped that by the time the third core is installed, we will be down to a cost which is going to be comparable to some of our other plants. 10 years later, in 1973, a group of private companies was again looking at thorium reactors and found that a demonstration plant using molten salts was worthwhile. But the technological uncertainties would need to be resolved and decision points reached that would permit development to proceed with the necessary confidence. Basically, they were unsure how well it would actually work, and if it was worth the investment. The consortium also identified a number of factors which tend to limit further industrial involvement, such as commitments to existing designs, lack of investment in supplying thorium fuel, the overwhelming experience in operating existing designs, which was comparatively lacking to thorium liquid salt designs, and the less advanced state of these new designs, and lack of clear solutions to known major technical challenges. So there were a number of significant technical and financial uncertainties, with no clear answers available, which made proceeding very risky. But what about bombs? While thorium reactors generate essentially zero plutonium, the material of choice for most nuclear weapons, they do excel in making another, tritium, particularly if they're using molten salt fuels. Thorium reactors may not produce one specific type of weapons material, but they produce a lot of another. So, did development of thorium reactors stop because they couldn't make bombs? No. Like we saw with Indian Point abandoning thorium after one cycle, and a consortium of eager private companies, it came down to the money. Thorium was more complex, had more technical challenges, and wasn't cost competitive compared to the uranium designs. So this one is busted. One of the main interests in thorium from the beginning was the fact that people were worried about the available supplies of uranium running out if a whole bunch of big new nuclear reactors were built. Adding thorium as a fuel source could diversify the supply, and even better since there should be more thorium available to mine compared to uranium. On average, there is about 3 times the amount of thorium in the Earth's crust compared to uranium. So in the strict technical sense, this is confirmed. However, we need to look beyond just the average numbers. Like uranium, thorium is not evenly distributed around the world. That means it's not useful if it's difficult or impossible to mine. In the case of thorium, it is not really extracted on a commercial scale, but more as a byproduct of other rare earth element recoveries. Because thorium is not the primary target of mining on a large scale, estimates of available thorium reserves are difficult to quantify. Nonetheless, despite the fuzzy numbers, the NEA and the IEA have estimated the world's economically mineable thorium reserves to be around 6.3 million tons, which is only slightly more than the much better known uranium reserves at 6.1 million tons. These figures are normally given on the low side, which in the case of thorium means that further exploration or improvements in mining, the material could increase further. Still, even doubling the available fuel for nuclear fission reactors using both uranium and thorium presents a pretty big advantage. One alternative and potentially useful source of uranium and thorium is is in the oceans, where the dissolved elements can be filtered from the water. In the oceans, however, uranium is much more concentrated. There is about 82,000 times more uranium than thorium, or about 4.6 billion tons of it compared to only 56,000 tons of thorium. At this time, ocean extraction is not competitive to mining on land, but there is always the possibility that that may change in the future. So this one, in the strictest sense, is confirmed. There is, on average, 3 times the thorium available for mining on land. But there isn't 3 times the amount that is known for economical extraction, at least not without further exploration for deposits. This really depends on 2 things. First, what is considered safe, and second, what elements make up the nuclear waste. Nuclear waste, particularly spent nuclear fuel, is dangerous when it is first removed from the reactor because it is highly radioactive, giving off various radiation that requires it to be covered or buried to protect it from people in the environment. Over time, though, the radioactivity declines until eventually it is about the same level as it was when we dug it out of the ground. This is a good way to define whether it is safe, when it reaches the same level of radioactivity as it was when we mined it out of the earth. The length of time it takes for nuclear waste to return to this, though, depends on the amount and types of elements in the waste. Some become less radioactive more quickly, within a few minutes or hours or days. Others take 10, 100, or thousands of years. Uranium and thorium fuel will create different waste products, which means they will behave differently. Under ideal conditions, thorium creates fewer of the very long-lived radioactive waste products compared to uranium. These are the elements that stay radioactive for tens of thousands of years. Since thorium creates less of these elements, it substantially reduces the amount of waste and length of time that the waste from thorium is dangerous. It also means that thorium waste can be about 10 times less radioactive when it comes out of the reactor. All this makes it much easier to store and handle compared to traditional uranium waste. However, after about 10,000 years, the radioactivity levels of both uranium and thorium are actually about the same. But for times less than 10,000 years, which is the time frame we are probably most concerned about, the thorium provides a significant waste advantage. It is also unfair to say that this benefit is unique to thorium. The comparison works well for uranium waste from traditional reactors, like the majority that are operating today. But just like there are designs that have been demonstrated using thorium, there have also been designs demonstrated using uranium that are just as effective at essentially eliminating the very long-lived elements from the waste. One more thing to consider is that not all thorium reactor designs run purely on thorium. Many designs use thorium supplemented with uranium in order to ensure sufficient power can be generated. Under these conditions, the very long-lived waste products will still be generated by the uranium, essentially undoing any short-term waste advantage given by the thorium. So our myth is technically confirmed, but needs to be slightly modified as to not be so misleading. Waste from purely thorium reactors is safer after 500 years compared to traditional uranium reactors, since similarly advanced uranium reactors achieve the same thing, and after 10,000 years it's all about the same anyways. Most nuclear weapons are created by either uranium or plutonium. The first bomb dropped on Hiroshima, Japan was a uranium design, and the second on Nagasaki was a plutonium design, which ended up being the preferred material. As a uranium reactor runs, it produces plutonium as a byproduct of its operation. This plutonium is naturally consumed while the reactor runs and actually helps the plant produce more energy. It is also possible to take the fuel and separate out the plutonium in a very pure form and reuse it in the reactor. It is also possible that the plutonium could be used to make a nuclear weapon. That's what's called nuclear proliferation, and it is to be avoided. In a pure thorium design, due to the nuclear physics, it is essentially impossible to generate any meaningful plutonium. However, thorium reactors work first by converting the thorium into uranium, and then using that uranium as the actual energy source. Just like it was possible to separate out the plutonium, it is possible to pull out the relatively pure, freshly converted uranium from a thorium reactor. This is not a bug, but actually a feature. A number of the thorium reactor designs rely on this uranium extraction method to operate efficiently, separating out the uranium and then reinserting it into the reactor to make more energy. The fact that plutonium is typically used in weapons is more historical than anything, mostly because of the uranium-plutonium route that was followed first. In 1966, Lawrence Livermore National Lab, one of the early nuclear weapons facilities in the US, stated, "Uranium-233 has been shown to be highly satisfactory as a weapons material, and if the existing weapons designs were based on uranium-233, Lawrence Radiation Laboratory would have no interest in switching to plutonium," meaning the only reason that they are using plutonium for weapons is because they were developed first. To emphasize this point, in 1955, the US successfully set off an experimental uranium-233 bomb as part of Operation Teapot. The test was generally a success, but not pursued any further. It's not that thorium reactors can't make materials for bombs, quite the opposite. It's just that there is less experience and no desire to go back and develop new ones, which could be expensive and politically questionable. So this one is busted. Safety is always at the top of the list when it comes to nuclear plants. Previous accidents at 3 Mile Island, Chernobyl, and Fukushima have demonstrated the need for proper design and safe operations. While today's operating nuclear plants have a very good safety record, most rely on complex safety systems and operators to take actions at the right time. There are certain things that can be done to improve this, such as passive safety systems that don't require the operators to do anything. Thorium reactors are often designed using liquid fuel that is pumped through the reactor. Liquid fuels offer more efficient energy extraction, improved heat transfer, and perhaps most importantly, can be operated at low pressures, close to the pressure you might find in your kitchen faucet, compared to the upwards 150 times the atmospheric pressure routinely used in traditional reactors. This means the heavy and expensive piping and reactor vessels are much simpler to manufacture and construct. It also means that if there's a leak, reactive steam won't explode outward because the liquid fuel is operating at a much more manageable pressure. Liquid thorium reactors can also be designed in such a way that if the temperatures get too hot or power is lost, a simple drain plug will melt, causing the normally liquid fuel to literally drain out of the reactor and disperse into tanks where it can be passively cooled indefinitely. This requires no operator action and allows the design to be inherently safe through simple physics. Another feature is that the volatile fission product gases can be pulled out online and contained separately, meaning there is much less buildup of dangerous radioactive material that could be released. The only problem with these features, better fuel utilization, improved heat transfer, low pressure, automatic drain plugs, and separating out fission products, is these are not unique to thorium reactors, but features of a design for molten salt reactors. And molten salt reactors can be just as easily fueled by uranium and get the same benefits. Because many thorium reactor designs are also molten salt reactor designs, proponents tend to mix the benefits. This doesn't mean that it isn't true, it just means that the benefits might be coming from the advanced reactor design, not the fact that it is using thorium. So on its own, this one is busted. There's a lot of misleading information surrounding thorium, which is a shame because it does have a number of real benefits, like expanding the potential sources of fuel that can be used. And in countries like India that don't have a lot of natural uranium, but a whole bunch of thorium, it looks like it could be a long-term solution. India is on the brink of a nuclear innovation that could redefine its energy future. But there's a problem. At the tail end of 2022, the spokesman for India's Department of Atomic Energy announced that its new advanced reactor, the ambitious prototype fast breeder reactor, faced additional delays and was extending its completion to late 2024.
So what's happening on the Kudankulam reactor? Your predecessor said that the delays will damage the reactor. Now the delays are happening because you're not able to commission the reactor. Is the reactor damaged? What is wrong?
It has been 38 years running and you still don't have the prototype fast breeder reactor, which is 20 years in the making.
While setbacks on nuclear projects aren't new, the prototype fast breeder reactor has the rather uncomfortable distinction of being in the running for the most delayed nuclear project in history, having been initially designed in 1983 and supposed to be up and running before 2000. Even by nuclear industry standards, things are extremely late. But this isn't just about missed deadlines, because this reactor is key to a much larger plan. Unlike most other countries, which focus on only a single technology, like water-cooled reactors, decades ago, India mapped out a distinct three-stage strategy for its nuclear program that is as ambitious as it is complicated. But it's one that could unlock centuries of cheap, sustainable energy for a nation with limited uranium and in desperate need of an energy revolution. So to find out how India, a country eager for progress, can get its nuclear energy program moving again, we need to answer a few basic questions. First, what exactly sets India's nuclear energy ambitions apart from the rest of the world? Why, despite its potential, is India's nuclear development stuck in perpetual delays? And perhaps most critically, is there a solution? Once we do that, we can put India, now the most populated country on Earth, on the Atomic Blender Nuclear Energy Leaderboard. Despite having a huge landmass and access to plenty of natural resources, India actually has very little of the fuel used in nuclear reactors, uranium, having only around 1% of the world's known supply. This would seem problematic for a country looking to massively expand its nuclear energy program to compete with the likes of China. What the country does have, though, is a whole lot of a related element, thorium. Thorium is an alternative fuel for nuclear power that was first explored in the 1950s and 60s, but was generally abandoned in favor of uranium, partly because of economics and partly because uranium was just seen as an easier route. Thorium does have the potential as a fuel source, especially for a country like India that holds as much as 25% of the world's supply, a lot of it literally sitting on the sands of its beaches. But there's just one small problem. Natural thorium can't be used in nuclear reactors directly. It has to first be converted into uranium. The trick is to be able to convert enough of the thorium to run a power plant. This gave Indian scientists an idea, and in 1954 they sketched out a master plan, aiming to make the most of their scarce uranium resources. The goal was clear: use what's available smartly and prepare the groundwork for something bigger. If they could figure out a way to convert the vast amounts of thorium into uranium, they'd have access to centuries of energy. But it wasn't going to be a direct route. To get to thorium, they'd have to do it piece by piece through a 3-stage plan. The first step had to be very efficient and use what little uranium the country had carefully. So physicists turned to the most efficient design available: heavy water reactors. Why? Because these plants could run on natural uranium. There was no need to develop and build the expensive facilities to enrich uranium like the reactors used in the US. It was a strategic move to avoid the large investments while getting started sooner. By the 1960s, this plan wasn't just on paper anymore. India bought its first nuclear plants, 2 relatively modest 200 megawatt heavy water reactors from Canada, and thus the first stage was set in motion. But these weren't just for lighting up homes and powering new industries. There was a dual purpose: generate electricity, sure, but also produce plutonium. When natural uranium is struck by a neutron, it doesn't always fission. Some of it absorbs the extra neutron and converts itself into plutonium through a process called transmutation. Once it's converted, the plutonium can be extracted and used later. So besides being very efficient with uranium, heavy water reactors excel at producing plutonium. And for this plan to work, India was going to need a lot of plutonium. But then in 1974, India's nuclear journey hit a very large speed bump. Just 2 years after their first Canadian-supplied reactor went online, the Indian Army tested an atomic bomb. The reaction from the international community was swift. Canada cut off all of its nuclear dealings with India, completely isolating them. But despite this, with the technology transfer from Canada already completed, the heavy water design would lay the groundwork for nearly all of India's future plants. And they didn't just stick with what they got from Canada. They scaled up, domestically designing and building reactors as large as 700 megawatts. Today, India operates 17 heavy water reactors, capable of producing nearly 5 gigawatts of electricity. That's an impressive fleet, but there's a catch. Because India's uranium reserves are limited, there was always a cap. The plan called for no more than 10 gigawatts using heavy water reactors. The plan was always to use the plutonium produced in these reactors as a stepping stone for the next stage in the grand plan. While heavy water reactors are great at making plutonium, they still end up consuming more uranium than the amount of plutonium they produce, which isn't great if you're trying to save a limited resource. But that's where a special type of reactor comes in, called a breeder reactor. By arranging the plutonium in the center, it can operate like just any other nuclear plant. And instead of using water to cool it, this design uses liquid sodium. It turns out this arrangement efficiently produces a lot of neutrons, many more than the heavy water reactor. So many that if we surround the plutonium with natural uranium, it becomes remarkably good at converting that uranium into plutonium as well. By using this arrangement, there are so many neutrons flying around that the amount of uranium converted into plutonium in the blanket is actually higher than the amount of plutonium fuel it consumes in the middle. It's called a breeder reactor for a reason. It produces more fuel than it consumes. And this isn't some theoretical dream either. Countries like the US have demonstrated this design works in the past, operating the experimental breeder reactor 2 until 1994. France operated its massive Super Phoenix breeder reactor, and Russia continues to operate 2 breeder reactors, having started up the latest in 2020. This design is at the center of stage 2. By feeding plutonium from the heavy water reactors and surrounding it with natural uranium, the breeder reactor creates an increasing feedback loop of plutonium, while still efficiently producing electricity. India aims to join this exclusive club with its own design, the prototype fast breeder reactor. But as with any ambitious plan, challenges are waiting, and this new reactor is a lesson in ambition meeting reality. The prototype fast breeder reactor was supposed to be a scaled-up version of its predecessor, the fast breeder test reactor. I know, very creative names. But as often happens, the devil was in the details. Scaling up meant dealing with a lot more of the sodium coolant, not to mention the specialized fuel and ensuring the integrity of all the components involved. Sodium, while excellent for cooling and efficiently making more fuel, comes with its own set of challenges. Unlike water, which is used in reactors around the world and is well understood by pretty much everyone, sodium is much more difficult. Sodium reacts violently when it contacts water, so even small leaks due to simple things like corrosion can cause devastating problems. In order to prove that this new design could operate safely, India had to put enormous efforts into research and development. Test loops and rigs were built to demonstrate components would work as intended. Experience from other operating breeder reactors in the US, France, and Russia also led to significant design changes over time, further delaying the project. There was also pressure to simplify the design and ensure economic viability. After all, the goal wasn't just to build a single reactor, but to build a whole fleet of them. This meant that the design needed to be both simpler to construct and cheaper to run. India's commitment to self-reliance added another layer of complexity. Opting for domestic design and fabrication meant the country was largely on its own to develop the technology required. All of these factors led to the project's spiraling costs and nearly quarter-century delay. Despite these challenges, the Indian government's support hasn't wavered, with budgets continuing to fund the first startup expected in 2024. While skeptics might point to the continual "it'll happen next year," there's no denying the importance of the prototype fast breeder reactor, because its success leads to the third and final stage of India's grand plan, thorium. While thorium has had a bit of a resurgence in popularity elsewhere in recent years, it's always been part of India's original plan since the 1950s. Thorium can act as an efficient alternative fuel to uranium. And just like natural uranium can be converted into plutonium in breeder reactors, thorium can be converted into something just as valuable, uranium-233. Since India has massive reserves of thorium, you can start to see where this is going. By replacing the natural uranium and instead introducing thorium into the blanket in the breeder reactors, India plans to convert it into usable uranium-233. The final stage is to then take this newly created uranium-233 and put it in the center of its own breeder reactor, and as you probably guessed, surround it with more thorium. Once this final cycle is self-sufficient, there's no need for the first two stages anymore, and the process can go on literally for centuries. This makes India unique in that it's the only country with a national long-term plan of operating a fleet of nuclear reactors powered by thorium. So why has India's journey towards this sustainable future been more of a slow marathon rather than a sprint? Well, from the beginning, India decided to take the road less traveled. After first importing reactor technology from Canada, India set its sights on achieving self-reliance. Developing, designing, and deploying its own nuclear technology is a bold move, given the complexity of atomic power. India is full of brilliant minds and some of the best scientists globally, but even the most ambitious projects still need a helping hand sometimes. The only other country operating a large breeder reactor today is Russia, which could at least in theory provide valuable insights and cooperation. However, that's likely dependent on diplomatic relations between the two, which as we've seen can change rapidly. Still, India's commitment to internal development means they're reluctant to seek potential collaborations. But India isn't alone in its nuclear ambitions. Around the world, private companies are pushing the boundaries of nuclear technology. Take Oklo in the United States. The California-based startup is building on the legacy of breeder reactors, aiming to bring efficient, small-scale plants to life. Then there's Copenhagen Atomics, which is working on plutonium-fueled thorium breeder reactors, just like India, only on a smaller scale. The question then is, can India navigate through the technical mazes and bureaucratic hurdles that lie ahead? After all, India's ambition isn't just to be a member of the nuclear club, it's to lead it. Now let's see how India, a country forging its own path, does on the Atomic Blender Nuclear Energy Leaderboard. Starting with size. India currently produces just over 40 terawatt-hours of electricity annually from its nuclear stations, which is just above average for countries with nuclear energy. So on a scale of 1 to 10, it gets a 6 out of 10. The country is still heavily dependent on coal, which makes up the vast majority of its electricity production. The remaining moderate amount of nuclear energy is spread thinly over India's massive population, accounting for just 3% of the total electrical output, which is well below that of other nuclear countries. So it gets a 2 out of 10. India has a decently long history of operating nuclear power, starting with its first reactor from Canada in the 1970s. However, performance hasn't been very good, with extended downtimes for maintenance and refurbishments, resulting in capacity factors that leave a lot to be desired. So for operating experience, it gets a 5 out of 10. Infrastructure. Because of its domestic ambitions, India has developed an extensive supply chain, research labs, skilled personnel, and fabrication facilities. While it has limited domestic uranium supplies, its plan to transition to what is essentially an unlimited supply of thorium means if it ever manages to get there, it'll be set for centuries. So it gets an easy 9 out of 10. Finally, growth. Very few countries have experienced as much nuclear expansion in the last decade as India, and more is expected in the future, with 8 reactors currently under construction and many more planned. However, like China, that growth has been more or less only keeping up with increased demand, rather than expanding nuclear share of the total. Still, government support is exceptionally strong, with long-term policies that aim to continue that expansion for years to come. So, it gets an 8 out of 10. Overall, that gives India a final score of 6, tying it with the United Kingdom, a score that could be improved if its ambitious plans for breeder reactors and thorium ever take off. And if you'd like to see how the UK, another country struggling with nuclear delays, did, you should check out this video. And thanks for watching, I'll see you in the next one.